Alright everybody, we're going to figure out, using our data, figure out the molar volume of the hydrogen that we formed in this lab. I'm going to use some data from a couple students that I got from first and second block, just to have a hodgepodge of data here. It will not be anybody's individual data, but you can use your data to compare. So I'm going to look at the volume here, the volume of the gas. This is coming from Sienna and Josh from first block. They got 25.323 milliliters. Everyone will definitely have a different volume there. We'll go ahead and change that to liters right away because we're going to want it in liters later. So 0.02523 liters. Difference in height between the two liquids. I'm going to get that number from Sienna, and actually I got that from somebody else, but I didn't write down your name, I'm sorry. So 296.0 millimeters. They originally measured 29.60 centimeters, and that was the difference in height that they found. So we're going to use this information to figure out the pressure of the hydrogen inside here, because we made hydrogen, but we also had water vapor, because this water is trapped. And as you read about in your book, when water is trapped above, or water vapor will form when it's trapped above water. So we have to figure out, keep that into account, because we're looking for the pressure of just the hydrogen, not the hydrogen and the water. So we're going to have to use combined gas law to do some figuring here. So I'm going to have P1 V1 over T1 equals P2 V2 over T2. One of them is going to be conditions in the room. So we'll just say this is the room conditions, and one's at STP. Since we didn't do things at STP, we can use the combined gas law to figure out what our volume would have been at STP. So in the room, the pressure of the gas, that's a little tricky, so we're actually going to wait on P1. V1, however, I have that original volume that Sienna and Josh gave me, and that is in liters, because we're going to want it in liters anyway, so I put it there. The temperature in the room was 22 degrees Celsius, so that gets me to 295. There's 22.0, so 0.0 Kelvin. Pressure at STP, since I had the pressure in the room to be in millimeters of mercury, so I'm going to use millimeters of mercury for that. The volume at STP, well, that's our big, what we want. We want to know what the volume of this gas would have been at STP if we were working at STP. Our standard temperature is 273 K, so this is STP. Standard pressure, standard temperature. This pressure is a little tricky though. How we're going to figure out this pressure is, first of all, we want to know the pressure of the hydrogen in here, just the hydrogen. So we have to take a look at what the pressure is of the atmosphere pushing on the top of this beaker here. So that's atmospheric pressure. The atmospheric pressure that we had in the first block was 735.6 millimeters of mercury. Go ahead and adjust this number based on if you're in first and second block. Since this difference in height, since there's a difference in height here, we have to take that into account. If the pressures were equal, then the water level in the oidiometer here would have been the same as the water level in the beaker. That wasn't true. So this difference in height is actually the difference in pressure. So we're going to use that difference in height to figure out what the real pressure is inside. And if we would have made more gas, this would have gone further and further and further down. And if the level was actually down here, that would mean the pressure inside the oidiometer is more than the pressure in the atmosphere. So the reason we're going to subtract this difference is because the pressure in the atmospheric pressure is more than the pressure that the hydrogen gas made. So we're going to subtract the difference in height. But that difference in height is in millimeters of water. So within this, I'm going to go 0.0 millimeters, but that's of water. So we're going to do a little conversion within this. For every, there's 13.595 millimeters of water for every 1 millimeter of mercury. So that is just a conversion that I know, and you can look up, but that's the conversion from millimeters of mercury to millimeters of water, because we can't subtract millimeters of water from millimeters of mercury. So we're going to do that conversion to figure out what the pressure inside of the oide is. That's what we're figuring out right now. Okay, so I'm going to do that conversion while I'm talking here. And you could be doing your own conversion, because everybody has a different height than Sienna and Josh, or whoever I took this from, sorry. And the pressure in the room is going to be the same for most of us. So I have 21.8 that this comes out to be millimeters of mercury. So I'm going to subtract that from the 735.6. That gives me 713.8. All right. So 713.8 is the pressure inside the oidiometer. However, the pressure inside the oidiometer is not just hydrogen gas. That is the pressure of hydrogen and the water vapor that was in there. So we have to subtract the hydrogen gas out, or the water out, sorry. So if I want to find just the pressure of the hydrogen, I want to take 713.8, which is water, hydrogen, and water vapor, minus the water vapor at this temperature. So what's the pressure of water vapor at this temperature? Well, I'm going to have to go to a slide to figure that out. This is a piece of paper that you have. You have a green sheet with water vapor pressure on it. It looks like this. And at the temperature we had was 22 degrees. So the water vapor pressure at that temperature is 19.8. So 19.8 millimeters of mercury would be the water vapor at 22 degrees Celsius. So 19.8 millimeters of mercury is the amount of pressure that water would put on that. So we're going to head back. My Mobi isn't working, so that's always fun. So I have lost all of my information. And when I lose all of my information, that's almost frustrating.